Good morning, students. Today I'm going to discuss about magnetic scalars and vector potentials. So this magnetic scalar and vector potential deals with the curl. So what I have sent you the list of properties of curl. So from that curl we're going to take two properties. So one is del into del v is equal to 0 and v is a scalar quantity. Del into del cross A is equal to 0. In that A is a vector quantity. So we need to discuss about scalar and vector potentials of a given curl equations. So here for first one, scalar magnetic potential. So how to define the scalar magnetic potential? So for that we need to consider scalar and vector components. So first we consider a scalar component, that is curl into or del cross del v is equal to 0. The same equation I have written, the del cross del v is equal to 0. M indicates the magnetic potential or the magnitude is equal to 0 and H is equal to del Vm. So this is similar to that of E is equal to minus del Vm. Okay, so instead of electric field intensity I am writing magnetic field intensity H is equal to del Vm, because this relates with the magnetic potential. That's why I have written in terms of H is equal to minus del Vm. So using in equation 3, use the above equation, that is equation number 4 in 3, will get curl or del into minus H, because here it is del Vm. So in place of del Vm I am going to write minus H is equal to 0, that is curl of H is equal to 0. This is from the table, so which I sent you yesterday. From that table I have taken curl of H is equal to 0. So that curl of H can also be equal to J. This is also same. This also I have taken it from the table which I have sent you yesterday. Curl of H is equal to J. That J indicates the current density. That J is equal to 0. That current density will be equal to 0. Curl of H is equal to 0 and that is equal to J. So J will be equal to 0. And this is your scalar and magnetic potential. So Vm A comma B. Magnetic potential at A comma B means at point A and at point B, that will be equal to I dot dl. Similarly, Laplace equation for scalar magnetic potentials. Already we are having an equation for divergence theorem, that is closed integral or closed contour integral of d dot ds, that is related with the electric field potential or electric field intensity, the d dot ds. So here I am writing in terms of magnetic field potential, that is B. Instead of D I am writing B dot ds is equal to 0. So B dot ds, closed integral of B dot ds is equal to divergence of D. There it is divergence of D, here it is divergence of B dV to volume. Curl into B is equal to 0. This equation I have taken it from the table, that B is equal to, we have an equation, B is equal to mu naught H. So starting only we have defined this equation, B is equal to mu naught H. In place of B I have written mu naught into H, but mu naught is not equal to 0. So divergence or del dot H is equal to 0. H we have minus del Vm. So in the previous equation or in the previous small derivation I have shown that del Vm is equal to 0. Del Vm is equal to H, or H is equal to minus del Vm. The same equation I have written here, equal to 0. So del dot del square Vm is equal to 0. Next thing is very important for the exam point of view, that is vector magnetic potential. So this is a very important question for the exam point of view. So nothing is there, you just have to concentrate on the two equations, that is del dot del into A and del dot B is equal to 0. You just put the relations. So B is equal to del into A, this is from the table I have written, and this also from the table, or else it is derived from the magnetic potential. Divergence of H or curl into H is equal to J. So in place of H we have an equation, that is B is equal to mu naught H. Here it is. So we need H. To get H, if you want to get H, you write B divided by mu naught is equal to J. So you transfer this mu naught to right side. So curl of B is equal to mu naught J. This B is equal to what? B is equal to this divergence of A or del into A. That is what I have written. So this is the equation is. Next, using vector identity to express left hand side rule. So this I have taken it from the curl property. Curl property I have taken del into A can be written as del into del dot A vector minus del square A into del square A is equal to mu naught into J. This I have taken it from properties of curl property. This is curl property. Okay, this is the final equation. So I have replaced del into A by del dot A vector minus del square A. This I have taken it from curl properties. What I have sent in the previous class, you just refer that curl properties. Okay, and this I have taken it from the last class, yesterday's table. So what I sent you in the yesterday, from that table I have taken the relations. Look at this. You just have to remember these two equations. So after that you need to substitute the relevant equation for the letters or for the values or for the magnetic potentials. Okay, this is what about the vector and scalar magnetic potential. Thank you.